So I want to discuss the properties of this function, which this function J star sheet, since this will be, we will use it many times. First, I want to make a remark. So I defined it in case of open embedding. Sheik, perverse of U to perverse of X. Now, open, in general, I study X is algebraic variety. I never assume that it's non-singular, but the idea is that, in fact, all computations usually you try to reduce to non-singular case, and you do it in the following way: that if Z in X is closed, then you can identify d of Z is equal to just dx Z. So you can think about our elements of the derived category of Z as just elements in the derived category of X, which are supported on Z.
So I want to answer.
Yeah.
I ask, what is D now? Is it Sheaves, Perverse, right?
Where?
D of Z.
D of Z, so this was standard, so D of X is by definition dB of Sheaves of X constructible.
Okay, good. Okay.
Yeah. So this will be standard notation. And after this identification, perverse of Z is equal to perverse of X Z, and so on. And the same is with D models. With D models, it's even more drastic that for D models, they're in fact defined, well defined only for non-singular varieties. And so for singular varieties, we just give this is the definition of left-hand side. One should show that it doesn't depend on embedding, but that's easier. So hence this open thing I can immediately translate to the following things. Suppose I have S and X locally closed subvariety. J is in corresponding embedding. Then I define functor J star Schlick from perverse sheaves on S to perverse sheaves on X. No, just the simplest way is the following: that it's locally closed, so there exists some open neighborhood where it is closed, and then you identify perverse sheaves on Z as perverse sheaves on U, which are supported here, and then perverse sheaves on. Okay, so.
What is the closed set that you take? In order to identify, you need to have a closed set.
Yes, Z is closed here. So it is just the same thing. I'm saying that there is no difference. You can consider open sets, or you consider locally closed set. It's easily go from one to another. Just
You explained this, I think.
okay. So now, so last time I wasn't quite careful. So let me now define. So suppose I have some S in X locally closed, and I have sheaf P on X perverse, and I consider J star sheaf of P F on perverse sheaf on X. And now I would like to characterize sheaves which I will get in this way. So what is clear about F is that support of F lies in closure of S. Now F restricted to S is equal to P. Now, so here I want to say, what does it mean F restricted to S? So the idea is that exactly what I said before, that if for general F, there is no notion of F restricted to S, because there are different restrictions. But if I know that S is open in support of F, then it's easy to see that J star of F will be equal to J sheik of F. J. So if support of F, if S is open in support of F, S is open in support of F. So precisely this kind of consideration shows these facts, because you first restrict F to open neighborhood, and then S becomes closed subset. And for closed subset, the claim is that for closed subset, J star and J sheik are the same.
And everything is independent of the chosen open set.
Yes, of course. Okay, so that's why I denoted F restricted to S. And second, so now the claim is that claim is the following conditions are equivalent. Conditions equivalent for P.
So just to clarify, there is nothing special about F being perverse here. You can play these games each time that F is.
Yes, this is this is
Yes, okay.
independent. This, yes. So first is that so P is so we assume that so P is perverse sheaf, support of P lies in S bar. So then the following conditions are equivalent. That first is that P does not, P is equal J star sheik of F, where F is restriction of P to S.
I think that you want to write the following are equivalent for. You think
that excuse me, F, excuse me, you're correct. So F is equal to J star of P, where P is equal to F restricted to S. Second condition that F does not have submodules and quotient models supported on the boundary on ds, which is S bar minus S. Okay, and this is more or less okay. So I will consider this. Let me prove this thing. So that's we use. So first, in one direction, if F is equal to J, so we have J sheik of P into J star shriek of P. This is embedding, this is epimorphism into J star of P. So I assume for simplicity that J is affine. So all these are just models. Otherwise, you can easily do the same considerations, but so assume that J. So this all is correct always, but let's assume that it's affine for simplicity. So then, so this is an embedding, this is epimorphism. So hence this module doesn't have submodules supported on the boundary because of adjunction argument. This model doesn't have quotients which are supported on the boundary. So this shows that this doesn't have submodules and doesn't have quotients which are supported on the boundary. Now, conversely, suppose we have some f, and we do not p is equal, f is restricted to s, then we'll have f is mapped into J star p is mapped into J shriek. So by adjunction, since f restriction to s is equal to p, then by adjunction you have morphism here, you have morphism here. And this is standard embedding. So then, if f doesn't have yes, so then I claim that f is embedded, that this is an embedding. So why it is embedding? Because the kernel of this morphism is supported outside on the boundary. Since if you assume that f doesn't have submodule supported the boundary, this is an embedding. Similarly, this epimorphism. So then f is this thing. Okay. So this is condition 1. And the third condition here is that for any strata S I which lie in the boundary of S, we have conditions that if you have x in Si and dimension of Si is equal to I, so we have that Ix star of f is concentrated in dimension less or equal minus I, and Ix shriek of f, no, minus I plus 1, minus I minus 1, and I shriek of f is concentrated in dimensions more equal I plus 1. So,
do we assume that S is the smooth part? Is S smooth now?
No.
No.
No,
Then
S
all
is...
the strata lives inside the boundaries.
No. So first of all, no. So the idea is that so first of all, what does it mean, strata and so on? So F in principle has some stratification. For F, there is a stratification, which smooth stratification where dimension of Si is equal to I. Some of strata will lie inside S, some of strata will lie outside of S. And F is smooth with respect to this stratification. That's standard thing. So now we restrict to this thing. So perversity condition is that for any strata, you have here less or equal to minus I, and here is more equal to I. So now the claim is that these conditions are equivalent to the conditions that for stratas which lie in the boundary, you have slightly stronger condition, one more condition. And in fact, even so, this condition corresponds to this one, and so here there are two conditions. So doesn't have quotients correspond to this one, and doesn't have submodels corresponds to this one. Yes, and it's very easy to argue. Just the idea that suppose that this condition so in interesting directions, that if this satisfies that this doesn't have submodels, so suppose this condition if it doesn't have submodels, then this condition satisfies. So suppose that this condition doesn't hold, then we have consider set of smaller dimension where it doesn't hold, and consider then we know that this dimension will be less or equal to minus I, and suppose it is not less or equal minus I minus 1. It means that it's exactly equal to I, and then we consider this tau, we consider f is strict to this I strict as I of f. We consider, so it has component in dimension I, so let's denote this hi. Let's consider truncation more or equal, yes, more equal I of this guy. So this will be a local system. Let's note this Li, local system shifted by, so this perverse shift on Si, and by adjunction you have morphisms from F to J Si to X of this Ai. But this means that F is that F has quotients which are supported on.
You take Li, and then what
I take this Li, more precisely, not this. This is perverse shift on Si.
Then push it to X.
I push it to X, and then there exists a morphism from F to this guy.
It's a star push, it's a J star of Li.
It doesn't matter because this is minimal dimension, so it doesn't matter whether it is J star or J sheaf.
Thank you for
So, but I push of course star. So the claim is that this then gives non-trivial morphism from this perverse shift to this perverse shift, and this contradicts the conditions that F has no quotients. Okay, so this is effectively very easy argument, and somehow some non-triviality of this argument because we have this strange abelian structure on these shifts, but when you look at from the point of view of D models, it's just extremely straightforward argument, just nothing here. Okay, so this is the way to check some F. Okay, so now I want to give some additional constructions, Deline's construction.
The whole point here is that the intermediate extension of perverse sheaves it's not just perverse, it's super perverse, it's extra perverse. This is
yes, it's not intermediate. It's so intermediate usually. Yes, this is okay. Perverse extension, intermediate extension. So usually when you consider. No. Yes, this intermediate extension. Yes. Yes, so the claim is that intermediate extension you can describe by properties. Now I want to give also the unit construction of intermediate extension. It's also useful. J star sheaf of P. Again, it's idea, so I will give it only in simplest case, so it's not really. So suppose I have, so I have my S, which I denote Sn, and on its boundary I have some, so it has some, suppose it's non-singular of dimension n, then on its boundary you have some components of n minus 1 and so on. So you have some stratification, Sn minus 1, Sn, Sn minus 2, and so on. And then I can consider the following open sets. Un is equal to Sn, Un minus 1 is equal to Sn union Sn minus 1, and so on. This is a sequence of open sets. Un contains in Un minus 1 this in U0, which is equal to X, or equal to S bar at S bar. I can assume that S is open. Okay, it is. So these are open subsets in S bar. Okay, so let's assume that X is equal to S bar. Okay, so I have sheaf here, and I would like to extend it to sheaf on X. What I will do, I will extend it one step by step. First, I will extend it here. So now my sheaf here is satisfies its perverse sheaf. Satisfies this kind of conditions. For instance, that J fibers of J star have bounded dimension. So consider P. Now let's say P prime is equal to J, so from Un to Un minus 1 star of P. So extend it once. Then if I look at behavior of this sheaf, it will not be usually it might be not perverse, but it's almost perverse. Namely, this condition, which is here, less or equal to I, it might deteriorate by 1. And so then what you do, then you just cut off, you take tau less or equal of this thing. So you just cut this off, this extra piece which appears, and then you continue this operation. You then go to Un minus 2, again, cut it off.
You're not losing information in this way?
What?
You're not losing a lot of information in this way? What are you truncating?
You truncated the last element, which is, so to say. Okay, so as a result, you'll get, you will come to X, and this will be exactly the same. The same function. So sometimes it's convenient to use this description. Yes.
That's a lot.
Why aren't perverse shifts resolved
By these operations, exactly.
By what operations?
Star.
No. Why is they perverse? Why is they? No. So they're perverse. So they are. No, yes, you're correct. So, No, I shifted around. So let's. So the idea is that no. Yes. So no. Okay. So let's, for simplicity, assume that all this. Just one moment. No, this is okay. What says not correct? Just how to formulate it. Okay, so let's construct family. So I have un minus 1, and so on. They construct Pn, which is just Pn minus 1, and so on. So, and I construct so P by induction. Pi, I consider J star of Pi plus 1. And I just look at this guy. So this guy on UN, it is perverse sheaf, it satisfies some conditions. On UN plus 1, okay, so suppose this equation is of, okay, on UN plus 1 it also satisfies, it maybe not satisfies this condition, but so the idea is that here we would like it to satisfy slightly stronger condition. So I take, okay, so I was not correct, so here I should take tau more equal this I plus minus I minus 1. No. So this is for J star.
Maybe we just.
No, it's.
Can you just explain one step?
Yes.
It's not important. I mean, this inductive procedure is okay.
Yes. So.
It's okay.
So you just consider one step. So consider J star of P, and consider its fibers. And so outside on the boundary, these fibers will be on components as I. It will live in dimension more equal to I. And then what I want to do, I want to consider tau less or equal to I. On Si, live at dimension more equal minus I. So I want to consider tau less or equal minus I minus 1. So I cut this extra piece which I don't like. So I don't like it because I know what I want to get in the end.
This truncation is truncation within perverse category?
Yes, truncation, no, truncation is...
Stupid truncation. Is it stupid truncation or perverse truncation? Because it's clear that
Yes.
you want to stay in perverse sheaves. I mean, that's what Timo was
Yes,
saying. You're not
yes,
moving
exactly.
up.
No, but no, this is truncation usual category.
Usual truncation.
Of course.
Now this is shocking. So you go out of the perverse category.
No.
afterwards.
So the Dean's construction was invented to describe
For IC.
what is for IC sheaf. So he started with local system on open set and then wanted to describe this without saying perverse sheaf. So he used just usual truncation. So here you're correct. So I was not careful enough to say that this truncation is just usual truncation. So in usual language, you can describe this.
So this is some kind of the elementary approach to the construction.
Yes.
And it can be done if you are Dealing.
Yes, it is. So, and sometimes it's just convenient to use because it's because it's elementary. So yes, you're correct. So here you consider, okay, I will do it one step. So you consider J. Okay, let's, so the in effect, of course, used it in case when on all intermediate steps, you have local systems. So our stratification is such that all these things are local systems. And then you just define, you consider J star P is restricted to this Sn minus 1. And then you cut it, you consider tau. Yes, no. You consider tau less or equal minus I minus 1 of this sheaf. Now, this thing on UN, on S, is just identity, doesn't do anything. But on next strata, it cuts a little bit. And then with this new sheaf, you extend it to next strata again, and consider
So in the middle, in the intermediate steps, you don't have perverse sheaves, but in the end, you will get. Is that what's happening here?
No. On any seek. Yes. On each step, you have perverse sheaves, but more than perverse sheaves. You have perverse sheaf, which is perverse on original set, but on all other things, it is a little bit better than perverse.
So this truncation preserves the category of perverse sheaves. It just makes
Yes,
it
yes.
better. All the
Yes.
models always make sure that this condition holds.
Yes.
But do you assume that on your original open set was a local system? Not. It could have embedded components, right?
Okay, so they consider it only case when it's local system, but as I understand, it just works always. Okay, I will leave it as an exercise. Okay, so and now what I want to do some example, just to see how it works. Just to see, for instance, that this factor is not exact. Why it is not exact, and it's something which. So the simplest example which we consider is just J C star to C. Embedding of C star, open embedding, and I would like to describe what's going on in this case, or I prefer to write it as A1 to A1 star. So here consider on C star I consider perverse sheaves, but I can consider local system because outside of 0. So if there are some singularities somewhere far away, then they don't matter. So I consider that P is local system shifted by 1. L is local on C star. Now, what is local system on C star? It is just completely determined by monotony operator. So you have just vector space V, which is L phi by 1, and you have monotony operator V to V, inversible operator. Now, if you have one operator, you can decompose it with respect to eigenvalues. So you can assume direct sum M has one eigenvalue. Now, first claim which is easy, that if lambda is not equal to 1, then J shriek of P is isomorphic to J star of P. So you'll get system which, so outside of 0 you know it, at 0 it has 0 fiber, 0 co-fiber, everything is 0. And the proof is very simple, just the thing which we use all the time, that if L is a local system on C star, then if you consider its image and consider the fiber at the point 0, then this will be equal to the invariance of monodromy. Just as I explained this, you can compute this as just cohomology of your local system, and cohomology in this case will be just, so in this case just H naught, so invariant section, so it will be just invariance of monodromy. So if lambda is not equal to 0, then there are no invariants, so the fiber is 0. And then by duality, this also implies that co-fiber is 0. And so then this is an isomorphism. So, but interesting case is when lambda is equal to 1. So then L, our system is just, our local system is just that cell. So let's consider first trivial, then L is equal to C. Okay, C. Yes. So lambda equal 1. So then this M is Jordan cell. So, and then we can assume that M is just one Jordan cell. We want to of length L. And first you consider case L equal 1. So what will be in this case? So let's define, let's consider what is J star of L. Okay, so let's be careful of L of 1. Then the claim is that this is a perverse sheaf and it has the following exact sequence. So first of all we have embedding of here C constant sheaf, C on C shifted by 1. And here you have delta, where delta is just delta skyscraper shift at 0. So the claim is that in perverse category you have this exact sequence. So you have embedding, consider direct image of this sheaf. Then you have first of all morphism of this sheaf, and this is perverse sheaf. And quotient will be this guy. This is again perverse sheaf, which is just skyscraper shift at 0 without shift. Yes, so now by duality for G star of L, for G shriek, by duality you have dual system. C so these two things are irreducible perverse sheaves. So this perverse sheaf is glued from this and this guy, and this also glues from this guy, but in opposite direction. Now what is morphism from here to here? It's quite clear that this morphism maps this quotient to this sub. Okay, so in this case, J star shriek of constant sheaf of C star will be just constant sheaf of C. So this operation maps trivial sheaf into trivial sheaf. Okay, so but if L is more than 1, then so how to compute it? So then suppose that consider system LL, which is Jordan cell of dimension L. So then the claim is that if you consider J star of L, and consider its H naught sections, then this will be one-dimensional. So it has, because invariants are just one-dimensional, despite the fact that the space is large, but if you consider the space of invariants, it will be. So this means that that fiber I0 star of this J star of LE will be one-dimensional. It will be isomorphic to, will be one-dimensional. Okay, so on the other hand, you know that functor J star is exact. And now let's consider, for instance, L2. For L2, you have natural exact sequences. Jordan cell, you have L1, 0. So if you consider J star of this, you'll get exact sequence. So okay, let's put here 1. Star of L1, L2, 0. Now we know that this guy is glued from two perverse sheaves, delta and 1, and this guy is glued from two perverse sheaves, delta and 1. So hence this guy glued from 4 to delta and 2 constant sheaf. And now, if you play, for instance, the Green's procedure, what you do, you cut off one of the delta. So as a result, you'll get, for this thing, you get the following Jordan-Gödel decomposition. You have C1, J star, so you have filtration. Okay, let me give the answer. So the structure here is the following: that you yes. So structure here is, let's denote this. I don't know. Let's denote this C of 1 is just a C of 1. Let's denote it C. Just constant shifted by. So structure here will be C. It's glued from C delta C delta, and then you cut off this delta, so you'll get something. So then it claims that J X star will have the following Jordan-Gödel structure: just C delta C. So it means that it has submodel, it has filtration, so that quotients are C delta C. And similarly, if you have J star of LL, then it has length 2L minus 1, and it's just, you have C delta, yes, C delta, and so on. So in particular, we see that this J star sheaf can have subquotients which are supported on the boundary. It cannot have submodulus, it cannot have quotient modulus, but it has, in this case, we see that it has subquotients which are supported there, which is very natural. It's very difficult to understand something about subquotients. About submodulus, it's possible. About quotient modulus, it's possible. About subquotients, it's okay. So just it's good to know this example because you know what you can expect. Okay, that's all I wanted to discuss. So, and it's a good exercise just to check for this particular case, just to convince yourself that you really can compute all this. Yes?
Could you say a couple of words about the spooky of fibers again? Because the last time.
I split fibers. Okay, so that. Okay, this fact I also wanted to tell. So Springer fibers. So you have G is the active group, and then you consider G check. So B is flux variety. You consider G check is subset incidence variety and G cross B. So which consists of pairs GB B, such that G lies in B. And you have morphism pi G check into G is proper. Okay, so now let's understand the, first of all, fiber of it. So first exercise, so computation. So claim pi is a small map. Okay, so I will leave it as exercise. So it means that you can give some very reasonable estimate on fiber, on dimensions of fibers. And so this, now I claim that this implies, so now on pi restricted to G regular, claim is a local system. No, pi. So pi from pi minus 1 of G regular to G regular is a principal W bundle. W, how it's called, covering. The W is a wide group. Okay, so first I want to explain what does it mean, what is W group doing here, and so on. This is related to the notion of the Cartan group. Of G. So usually Cartan group is defined as something up to conjugation, but it turns out that the Cartan group can be defined absolutely canonically, not as a subgroup of G, but as a group. Namely, let's pick any P, any Barrel subgroup in G, and let's say H is equal B mod U of P, mod unipotent radical. The claim is that this group is defined uniquely with no choices. Because if I have another group, B prime, then there exists given. So let's denote it HB. So we constructed, choosing Barrel subgroup, we construct some nice torus The claim is that it's absolutely canonically defined. So why? Because if you choose another subgroup, then there exists element G in G such that Rg B is equal to B prime. And this element G defines memorphism from B to B prime, and hence from H to HB to HB prime. Now the claim that this morphism is absolutely canonical, that doesn't depend on choices, because G is defined up to element which maps B into itself, the element normalizer of B. The normalizer of B coincides with B. So hence G is defined up to an element of B, but then this morphism so hence the morphism which is given by this element on HB is just identity. So hence this thing is well defined, it doesn't depend on choice of G. So hence for any two Borel subgroups, so we defined our HB depending on Borel subgroup, but for any two Borel subgroups we construct a canonical isomorphism. So hence this thing is absolutely canonical. Moreover, not only it's absolutely canonical, but it's also has canonical root system, because it was defined as embedded into some B. Root system, and not only root system, but also positive root system. In particular, the claim is that it has while group. And then it's easy to see that if you consider H H and G, so consider some embedding of G and G is a Cartan group, and consider all the set of Borel groups, containing H, then this will be canonically BH is a principal W set. We have canonical action of the group W on this set. This exactly means that this set, this G regular, pi minus 1 G regular into G regular. So fiber at every point contains W element, and in fact you have action of W on this algebraic variety, and this is a fibration. On any fiber it is principal. Any fiber is a principal W set. So hence, if I consider pi star of constant sheaf C of G check shifted by, I consider perverse sheaf, then this will be restricted to G regular. It will be just okay. It will be say local system with action of W. On the other hand, if you just consider this, we denote this P is equal pi star of something, then this will be, since pi is small map, this will be perverse sheaf obtained from this set G regular by extension, intermediate extension. So these exactly conditions which I described in the beginning of the lecture. This satisfies all these conditions outside of regular sets. On regular sets, it is okay. So hence, what happens is we have action of W on restriction of this sheaf to so let's denote this P is the restriction of this. So F is this sheaf, F by star of C of check tilde, and is restriction F to G regular denoted by P. So then we have Wx on P on one hand. On the other hand, F is equal to J star shriek of P. This is the canonical isomorphism. So hence, in particular, this implies that Wx on this sheaf. If it acts on these sheaves, it acts on all fibers and co-fibers of these sheaves. By fibers of these sheaves are just cohomologies of fibers of our morphism pi. And hence it acts on fibers of this sheaf pi, which has some kind of non-trivial variety. So once over regular sets, these varieties are very simple, just finite number of points on which Wx simply transitive. But over unipotent points, it is quite non-trivial. Okay, so maybe I will finish just say that in case what is B E is unit element is just B. So the claim is that, for instance, in cohomologies of B, you have action of W. So in this case, I know how to describe it geometrically. The idea is that our group G has maximal complex subgroup U. So if G is J-ln and U are unitary matrices. So U intersection with H, T is maximal torus in U. And then it's easy to show that you can identify B as U quotient by T. So for matrices, you just everything is. So this follows from the fact that B times U is equal to G. So this is called Evasion Decomposition. Okay. Now on this already is not algebraic, right? It is some kind of just usual topological.
You need to K. U is equal to K.
No, just U maximal complex subgroup. Just for in case of J-ln, it's just unitary group. That's why they're not by U. Now here I have action of W just on the right, because W normalizes T. So in this picture, I have actual action of W on the space. But this space section is definitely not an action of algebraic as an algebraic variety. It's just action on real variety. So, but this is just this action. But I don't know how to make this picture for other Springer fibers. Just when I first heard about Springer, so I tried to understand the simplest case. And in this simplest case, I understood that there exists actually action of W on cohomologies of this variety, because there exists action on just on variety, topological action. In general case, so in fact, in Kazhdan and Lustig, they had some kind of action. I think not of the whole group W, but for each simple reflection, they had some kind of topological.
You think this is vibration?
So I don't remember. In one of the papers, they had some. But so in general, even if you achieve this, and it's somehow not very natural, somehow this Lucy construction of perverse sheaves explains this action much better and gives possibility to work with this. As far as I recall, in Kazan Lustig, they can describe action of each simple reflection, but they cannot really prove that this forms representation of the value because it's too complicated. Okay.
K. K. Unitary group for GLN. Maximum